Now let's see how to use the principle of communicating bases with the sum of digits function. Now that we did it for factorial, we get back to sum of digits. So in sum of digits, we notice that each recursive call will handle one digit. So the idea is to split the work into pieces where each piece corresponds to one digit. So we take the initial number n here and we write it down as its digits. So each of the di's here is one digit. And let's call the sum of digits function s of n. And then we have the following invariant. We can split the work into two parts. We have s of n is equal to s of a part of the number plus the sum of the digits of the other part. So these two parts, we call the first part si and the second part a. So this here is going to be our invariant. Okay, notice that the part on the left of the equal sign is like a constant. It's during the whole calculation, it's the same. It's the Sn we're going to calculate. And on the right-hand side here, we have two parts that vary, and it's the sum that has to be constant. So in order to keep the formula true, when we advance in the calculation, we will, in the Si, increase I by 1. So the number inside here will reduce in size. And then the A prime is A plus di, the number increases. And then when I is equal to k, then this number is an empty number, which is 0. So sk is equal to s of 0, which is 0, and then A is the answer. So let's show an example of this. So with our favorite number, 314159, so here again is the invariant. Sn is the first part here, plus the second part. And we start here with S314159 is equal to S314159 plus 0, so we don't know anything yet. And then we remove a digit here out, and we add it to the accumulator, and we keep moving digits out here until finally we get to S of 0, which is 0, and the result is 23. So with this, we can now actually write our function. So in the function, we have then our two parts, which correspond to two arguments. So S and A. Notice here in the S, we're going to look at the inside of the S of n, because it's the number that we're going to be reducing in size, and the A is the accumulator as before. So in the function sumdigits2, with the arguments S and A, notice that if S is equal to 0, which corresponds to the I is equal to k, then the result is A. Otherwise, we have the recursive call. So we increase I by 1, which is reducing the number by 1, which is removing the lower digit. This is S div 10. And in the other part, we add this lower digit to A. So you notice, in fact, it's actually rather obvious, but using invariant programming, we have a very systematic way. And in fact, when we start looking at more complicated functions, you'll see that invariant programming is a really good support for making sure that things are correct.